So it's an honor to be, so thanks for having me. I will give 3 models of information processing, or more broadly of cognition. I was thinking how to connect them together, how to glue them, and I realized that maybe the methodological connections are the best way of connecting them. So I will start with some math. So I pick up some little but important results that are being used all over of the talks of other lectures and also in the papers that I'm going to present. So the first result will be from large deviation theory. Then I will talk about statistical learning, and then I will revisit the concept of entropy and mutual information. You have seen so much of it, but I want to go over this concept kind of more slowly in more detail to give us some detailed understanding of them. So large deviation theory is a subfield of probability theory which deals with improbable events, rare events. So to give an illustration, take a fair coin, flip it 1,000 times, and ask yourself what will be the empirical distribution of the heads and tails, and most likely it will be close to 500. That's what the law of large number tells us. But it is possible, not very likely, but it's possible that you will observe 3/4 of heads, perhaps. And the large deviation theory deals with the question: how likely is it that you will see such a rare events? So let me just formalize it slightly. Take a random variable, or the draws from a random variable from a distribution P, flip this random variable t times, define the empirical distribution to be just the frequency of occurrences of any possible outcome of this random variable. Law of large number would tell you that most likely that empirical distribution for large enough sample is going to be very close to the true data generating process. And I'm asking how likely it is that that empirical distribution happens to be something which is not close to the true process. That is called a large deviation, and there is something quite elegant about it called Sanoff theorem that tells us approximately how likely an unlikely event is. And it tells us that the probability of seeing an empirical distribution Q decays exponentially with the length of the sample at the rate that depends on both the empirical distribution and the true data generating distribution. And this thing here is good old Kullback-Leiber divergence that you have seen so many times. This is some sort of a pseudo distance of two distributions. So the bigger the deviation is from the true data generating process, more quickly the probability of seeing it decays with the size of the sample. Now don't look too much into the formula. I'm not very good with formulas. They don't help me that much. Kullback-Leiber divergence is some sort of a pseudo distance. It's not distance because the mathematicians made a convention that distances are supposed to be symmetric in the arguments. This one is not symmetric. You flip the arguments and the number changes. I'm not going to prove you the Sanoff theorem, but you will actually get all the tools, or you already have tools to prove that, at least informally on a page, and I will encourage you to try to do it. I mean, proving it formally with all the blows and whistles would be difficult, but the only difficult part in proving this result is to think about how many sequences are there with a particular empirical distribution. So all the permutation of one also give you the same empirical distribution. So it's a question about the number of the permutations. That's a combinatorial question. But that question can be answered approximately with a concept of entropy, on which that you know, and I will talk again. So once you understand well concept of entropy, you should be able to prove this informally on 1 or 2 pages. And I would encourage you to try to do those things, because if you are using this concept, you should really understand them intimately. So now, and I will be using that in one of the papers that I will cover. So the next thing that I'm going to talk about is statistical learning. Again, something that you are familiar with. So think of an econometrician. Yes, please. So there are many large deviation theory results. There are different limit, different asymptotics. So I think there is an answer in the large deviation theory that would probably relate to what you are asking that I don't fully understand. We may talk later about the exact result from the large deviation theory that you may be wondering about. All right, learning. So think of an econometrician. observes a sample of data points called here signals, x1 up to xt. These are drawn from some distribution, P, that the econometrician doesn't know and would like to learn about it. And this econometrician has a bunch of hypotheses. These hypotheses are parameterized by some parameter theta living on in some space. All spaces in all of my work are finite. And each of these hypotheses specifies a distribution of the signals X. So it's considering several distributions and is trying to learn which of these actually is the data generating one. Let the econometrician compute the maximum likelihood, so do the maximum likelihood estimation. So given hypothesis, he computes or she computes the likelihood of the sample and then chooses the hypothesis that maximize the observed sample. And a natural question is, what hypothesis will the econometrician choose asymptotically as she observes plenty of data? Now, if she is well specified, meaning that one of those hypotheses, say denoted here by theta star, happens to be the true hypothesis, happens to coincide with the true data generating process, good news, I mean the relieving news is that she will learn the true hypothesis asymptotically. Almost surely she will converge to the hypothesis that happens to be the correct one. And we know that that's Wald and other researchers in various forms. A more interesting case arises when the econometrician is misspecified. It's a more natural case where all of the hypotheses that she has happen to be wrong in that they do not coincide with the true data generating process. That's typical because our models are too simple. So the question is, what happens then? And so let us define the most truth-like hypothesis. And let's define that as the one which minimizes the Kullback-Leibler divergence between the true data generating distribution and the hypothesis. Of all of the hypotheses you find which is closest one in terms of Kullback-Leibler divergence to the true distribution. And then making my life simple, assuming that this minimizer is unique, a similar result applies. The econometrician almost surely converges to a pseudo-true hypothesis, the one which minimizes this wedge. Right? So,
and if it's not unique, do you converge to one of them?
No. Then it can. The statement becomes complicated. This is what White and Berg would tell you in details. You can, in a complicated way, cycle about it. I think then the statements are about the support of the process of your belief or your estimate. So it becomes more difficult.
But you would declare, you might cycle, but
you will be cycled on the arg min. No?
Yeah.
You will, yes,
Okay,
yes, but you will not. There is no convergence assured. There is no convergence assured.
This you can prove in 3 lines. You don't need to take it.
Correct, and this is what happened here. So actually, and the Sanov theorem will give you one of the possible ways of seeing why this is true. So it's just a combination of law of large numbers and Sanov theorem. So law of large number tells us what will be most likely the data set, the distribution, empirical distribution of the data set that the econometrician will observe. Well, it will approximate the true distribution P. And then for each hypothesis that the econometrician observed, for each theta, the econometrician asks, if Q theta were the true distribution, what would be the likelihood of a sample that I'm observing? Well, that's given by Sanov theorem. This is an exponential function of the size of the sample. So the hypothesis that maximizes the likelihood is given by the exponential function which decays least quickly, and that's the one that minimizes this Kullback-Leibler divergence. All right. So that's the connection between the important result of asymptotic learning and Sanov. And the last kind of pedagogical piece of math I want to show you is to discuss the concept of entropy that you have been exposed a lot to. I want to motivate entropy as a measure of a complexity of a random variable. So a dice has 6 outcomes, that's more than a coin, so it's kind of tempting to say that dice is more complex. So maybe the one measure of complexity is the number of possible outcomes a random variable has, but that's too of a course of a concept, because you can think of a fair and unfair coins. They both have 2 outcomes, but somehow the unfair coin is more predictable. So perhaps I would like to have a concept in which the unfair coin becomes kind of more predictable, more less complex than the fair one. And I'm gonna I'm going to extend the concept of complexity, which just counts the number of outcomes, to the random variables that have just some general distributions. So let's think not of the number of the outcomes of a distribution, but still think of the sequences that the random variable generates. So let's flip coin many times, and let's ask t times. Let's ask how many sequences it generates, and the number is 2 power 2t, whether it's fair or unfair. But I want to convince you that in some sense, and we have to be creative in that sense, an unfair coin is going to generate a smaller number of sequences. It's going to generate the number of sequences which grows with this rate. The number of sequences that an unfair coin generates is going to grow in the sense that I will clarify on the next slide at the rate which is smaller than 2. So let me try to clarify that. So let's sample in an ideal sense. Let's flip an unfair coin t times, and of course the number of sequences is 2 power 2t, but many of the sequences that I will observe will be atypical in the sense that they will be extremely unlikely. They will be less likely than other sequences. I know by the law of large numbers that I'm flipping an unfair coin, the empirical distribution of that sequence should be close to p. All the distributions that will have frequencies which are different from that true distribution will be extremely unlikely, and altogether the likelihood will be negligible. So what I can do is I can say, okay, let me give up on all the sequences as atypical distributions. They do not contribute to the likelihood very much, and I just want to understand how many sequences are there with typical frequencies, because those are the only ones that I will in practice observe. And it's actually an easy exercise to compute what is the number of the typical sequences. So if the distribution is p, I'm flipping the coin, then this will be the likelihood. I know how many times I will see head or tail. That's given by law of large numbers. So this is the number of heads or number of tails. Then I can take the likelihood of head or tail, and I got the likelihood of any typical sequence. Then I can go back to high school. I can play around with the logarithms. So I can just turn that into this. And I get an expression which is 2 powered to an expression which defines entropy, or it's an entropy with the minus sign. So what I'm just saying here is that the number of the typical coins grows exponentially with the length of the sample at the rate that depends on the distribution of the random variable at the rate equal to the entropy. So if I'm interested only in the typical sequences, then I got how likely each of that typical sequence is. Now they're all equally likely. The total probability is close to 1 minus epsilon. If they're equally likely, then if I divide 1 with this number, then I get the number of the sequences. And so what's happening is that the number of the sequences that have a typical distribution grows at this rate. Yes, please.
Sorry, I just missed why is that the thing that's the approximation? Like, what's the resolution?
So what you missed something about this line.
Yeah, the first sign. No, the first, yeah.
All right. Is there an approximation, or is this precise? I think this is actually this is an approximation because the sample is random.
No, yeah, but why? What holds? Like, a very stupid question.
Why this holds? So this is the probability of this is the likelihood of the sample.
Yeah.
And now the approximation appears because I'm using a law of large numbers. So suppose the coin has a 3/4 of probability of head. So I'm saying out of the 3/4 of the outcomes is head and 1/4 is tail. So then I take the probability of head, that was 3/4 here, and I multiply it with t power times 3/4, so that would be 750 if the size of the sample is 1000. And I do the same with the tails, and this gives me the likelihood of a sample. Okay. Thank you. So to wrap up, entropy is a good measure of complexity of random variable when you think about the samples of the draws from distributions. It tells you about what is the number of the typical sequences. It also tells you what's the distribution of the sequences. It's a uniform distribution with some very unlikely sequences, but on the set of typical sequences, a uniform distribution, each of that, and so the entropy then tells you about what's the measure of uncertainty over those sequences of random variables.
I remember correctly, Shannon made exactly that.
Yeah, this is of course, this is Shannon. I'm teaching Shannon's material here, yeah. So I was just, advertising the basic elements of information theory. And so the last thing that I want to show you is to remind you of mutual information. You have seen that, so let me just do that very quickly. Mutual information, now once we have agreed of having a measure of uncertainty of a random variable, is just an expected reduction of an uncertainty if you observe a correlate of a random variable of your interest. So you might be interested in the random variable theta. You don't get to observe it, but you observe an outcome of a random variable x, which is correlated with theta. Before you have observed that outcome, this was your measure of uncertainty. After you observe an outcome of theta, your conditional belief changes to a conditional random variable that has an entropy, an expected reduction of entropy is then the measure of information which was conveyed to you by observing an outcome of a signal. There are many ways that you can express mutual information, and let me advertise one which will be kind of relevant for something that will show up later on the slides. So a way to rewrite mutual information, and Rafa actually has mentioned that, is you can write a mutual information as a Kullback-Leibler divergence between a joint distribution between theta and x and a product of marginal distributions. So let me give a context to this alternative formula. So suppose you have observed a sample of both theta and x. The sample suggests that those two random variables are correlated, so you see an empirical correlation, but you kind of doubt whether this is really the case. Maybe this was just an accident. Maybe these two random variables are uncorrelated, independent, and you are observing that correlation just by luck or by accident. So you might ask, if these two random variables were independent, what would be their distribution? That would be this. And then you can ask, if this was the true distribution, how likely were I to see that empirical correlation? And this formula exactly tells you. So the mutual information measures how unlikely you would observe a correlation in a large sample if actually the true random variables were uncorrelated.
Via Sanof's theorem.
Yes, this would be the connection via Sanov theorem, yes. All right, enough of math. Let me go to economics, and I will start with the second paper because that's the one that I'm most excited about. So it's a recent paper we did with Arthur Robson and Larry Samuelson. It's something on the boundary of macroeconomics and decision theory. So you might not have thought that these two fields have a boundary. And we kind of stumbled upon this boundary. So what we are going to do is that we are going to study a macroeconomic problem. Now, if you really like macro, don't get too excited. I mean, by the set of the authors, we will not be able to do like serious studies on macro. So this is how we imagine macro should be done. And when we were thinking about this macroeconomic process, and we call it macroeconomic because it will involve many people, we figured out that some policies, optimal in a sense to be specified, can be represented as solution of Desiccek theoretic problems. So we have some bunch of representation theorems that tell us about optimal policies in a macro situation. Now, we were advised to study models that can be formulated under 2 pages, so I'm happy to report that we satisfied that with a large margin. So here is a very simple model. The model is here. Let me just jump to the model. So be there a continuous population, be there a discrete time, at each period t, each individual from that population chooses an action, and this leads to a stochastic return on her wells. So her wells at that given day multiplies by this factor. This return depends on the action chosen by the individual, but also by some random variable, by a shock at that period. So you cannot fully control the return to your wells. And the notation is a bit unusual. I could call this R of A and theta. I have chosen to introduce little u here. That's a log return. And I denoted it here by u, which is suggestive of utility. So I will end up with a representation where this function will be naturally interpreted as a utility. But here it's a log return, or a growth rate of your wells at a given period if you have chosen A and you have encountered a shock theta. The shocks are already drawn from a distribution. And we consider two versions of the model, the one with idiosyncratic risk and the aggregate risk. In the case of idiosyncratic risk, each individual has own realization of this random variable. So maybe Rava has a good day today, I have a bad day. Our shocks are drawn from the same distribution, but the realizations are individual. And we are looking for policy, in this case, just for an action from an action set that marks that if everybody chooses this action, the growth rate of wells in this population will be maximized. So that's this problem here. If you experience shock theta, choose an action A, then this exponential function is your return. By taking an expectation over all possible shocks, this turns it into an aggregate return of wells. The logarithm would turn it into the growth rate of the wells in the economy. And I'm looking into an action that maximizes this. This is actually a simple problem because the logarithm doesn't do anything here. This is just a monotone transformation. So the answer is trivial, and this is why this problem wasn't studied. You just choose an action that maximizes the expected return. But it turns out that there is another answer to the same problem, an equivalent answer, which tells us something about the structure of the growth problem. So to give you that alternative answer, I have to introduce a recent model by Andrew Kaplan and John Lee, which is kind of an exotic behavioral model. And I will claim that the solution of an exotic behavioral model introduced by other people in a very different context gives us the same action that maximizes the growth rate in our economy with idiosyncratic shocks. So this is a model when there is no growth, no dynamics, no population, just one person choosing an action. From an action set, she gets a payoff that depends on the action chosen and a shock. Shock is from an objective distribution that the decision maker knows. But the decision maker happens to be a wishful thinker, somebody who likes to fool herself. So this decision maker is endowed with a psychological technology that allows her to change her belief from the objective belief P to some subjective belief over the states that she's facing. So she's given that technology, but it's costly to manipulate yourself. Don't ask me why, this is the model of other people. So, but you can work on it and you can convince yourself of whatever distribution you like to at this cost. Once you have done your job of manipulating yourself, you choose an action, you enjoy a subjective expectation, expected utility, given the belief you have chosen, and thus this leads to a joint optimization both over the action and the belief. Okay, so that's the psychologically motivated model. This is again a Kullback-Leiber divergence. And so here is a result. It turns out that the three statements are equivalent. An action maximizes the growth rate under idiosyncratic risk in our model. That action, equivalently, is an expected utility maximizer with the objective prior and a utility equal to the return in our model. So that's a trivial result. But here is a third result. A wishful thinker with the objective probability P that she can distort as she wants, and the utility U would choose also this action. So what the wishful thinker would end up choosing is the action that maximizes the growth rate. Also, it is behaviorally equivalent with the expected utility, so meaning an analyst observing just the behavior of a decision maker would not be able to distinguish between a wishful thinker and an expected utility maximizer. That point is not entirely new, so Tomáš made a similar point in his job market paper in kind of a mirror image of the wishful thinking model. What I think is relatively new is the connection with the growth processes. So let me try to explain an intuition for why this kind of psychologically motivated model represents the action that maximizes the growth rate. So I'm back now in our model with growth. So think of this very large continuous population of people. Consider a finite horizon T. Most people will experience a sequence of shocks with a typical distribution, with the frequency of shocks very close to P. But there will be some very lucky people among us who will be experiencing an atypical sequence, a sequence that will have many good draws and few bad draws, and these people will experience a larger growth rate than other people. So think of a person who has experienced an empirical distribution Q of these shocks. There will be some people, there will be a fraction of such population for any finite horizon that you can consider. The growth rate of those individuals will be given by that empirical distribution. So it doesn't really matter what was the data generating distribution, it's the one that you have experienced that determines how wealthy you end up being. But of course the downside is that there won't be too many people if this distribution is very atypical. So the measure of people enjoying a particle distribution of shocks Q decays with the considered horizon T also exponentially with a rate given by Kluber-Gleiber divergence. This is the Sanov theorem here. Now luckily both of these things are exponential functions, so you can easily combine them, and you can ask them the following question: for any given empirical distribution, what is the total wealth of people who have enjoyed that empirical distribution? And it's going to be an exponential function of time with the rate given by the sum of those two exponents, that is with this growth rate given by the deviation minus the penalty for the rarity of having a particular level of luck. What is the aggregate wealth in the population? Well, that's the sum across all empirical distributions. So there will be people with a very large amount of luck, people with an intermediate amount of luck. Most of us will just observe a typical distribution. So you have to sum up over many exponential processes, exponential functions, but fortunately when you are summing exponential functions, you just can take the one with the highest exponent and you can ignore all the other ones. And so the growth rate of this whole aggregate wells is just given by the maximum over these growth rates is when you maximize over all possible deviations. And that was exactly the problem of a wishful thinker. And therefore, we are kind of getting a connection between the macroeconomic models and the decision theory representation. And the decision theoretic representation, even though it's equivalent to an expected utility, has a structure which is useful in thinking about the growth problem, because it gives you an insight about the dynamics of the wealth in this population. So for instance, you can ask what happens with the wealth inequality. Now all of these people have started with the same endowment. They are having same distribution of shocks, facing same distribution of shocks, same stochastic return functions, but some of them were lucky, so you get a growth concentration, you get a wealth concentration where those people with the optimal large deviations end up owning all the wealth asymptotically.
Just a question about this is true if your this divergence, the argument I mean is correct if the divergence is of order 1, right? Not if as you increase the time you start converges to P. Is that correct?
No, so for any time,
but then you're not in the large deviation regime.
so what happens is that the growth is effectively unfolding alongside a large deviation. There will be ever diminishing population of people who will be having an atypical distribution of shocks. The number of those people will be, or the measure of those people, it's a continuous population, will be decreasing exponentially pretty quickly, but each of them will have an extraordinary growth rate, and all their wealth together will be growing quite quickly. So what will happen is that asymptotically it will be a diminishing measure of people owning all the wealth. And this is true for any T. So it's just that since I have a continuous population, I never run out completely of those lucky people. And so if you are looking at, you can check in the round 10,000, you can draw a dollar, and you can ask what will be the distribution of the shocks this owner of the dollar has experienced, and it won't be the typical distribution, it will be the atypical distribution, the one which maximizes this problem.
I think I understand. I think the problem is, what if the solution of this problem gives you that Q is extremely close to Q? Then the large, then that probability that was exponential could much larger than.
No, this is a special case. Then I mean, this would be close to zero. So and then this person wouldn't have much of a growth advantage. So this can be a solution. So for instance, if I would make this log growth rate independent of theta, then the large deviations will not be really useful. And then I think it will have multiple solutions, but one of them will be Q being close to P. So I don't think anything wrong happens in settings where the maximizer is close to the objective distribution.
Just a technical question. Are you relying on the exact law of large numbers here?
Yes, so we are relying on the exact law of large numbers for the population size. And that is important. We were thinking about the finite population, and there might be interesting problems with it. So if you have an infinite population, a continuous population, we will never run out of people who are having this extraordinary luck. Now, if you start with 10 billions, you will run out of the people actually quite quickly because it's an exponential process. So you can then start thinking about questions like what is the short-run growth rate and what is the long-run growth rate. And the long-run growth rate with the finite population without any additional elements of the model will be smaller once you run out of those lucky people. Thanks for the question. All right, so you get what we like about the model of Andrew Kaplan and John Leahy is that the behavioral model, incidentally equivalent to explicit utility, has a structure which is informative of our macroeconomic questions. You could ask, what will be the distribution of the people who end up owning all the wells? And that happens to be the distribution of the shock that the wishful thinker would choose. And you could ask, what is the rate of concentration of wealth, how quickly inequality grows in this society? And that will be equal to the expense of the wishful thinker in this behavioral representation. So that was the case with idiosyncratic risk. And let me now tell you about the aggregate case, the case with aggregate risk, which I think is slightly, perhaps, we find it more interesting. So in the case of aggregate risk, all agents are subject to the same shock. So this random variable theta determines the returns is again drawn from some distribution, ID across time, but now Rava and me and everybody else is getting the same realization every day. And we again are looking for a policy that maximizes the growth rate of the aggregate wealth of this economy. The novel thing that happens here is that at this point, at this situation, it is advantageous for people to randomize. Because if people individually randomize, then whatever the realization of the shock is, some of us will have chosen an optimal action or well-adapted action to the realization of the shock. So it is advantageous for us to use mixed strategies. So let's just maximize over all mixed strategies. Since we are mixing, for a given aggregate shock theta, I can take an expectation with respect to the mixed strategy, and that gives me the aggregate return of the society on a day with the given shock. Logarithm turns that into the growth rate, and now I take an expectation over the possible shocks drawn from a distribution P, and I'm just looking for an optimal mixed strategy. So this is equivalent to a problem of Kelly, which is Kelly made important contribution to information theory and finance. So this is this modular relabeling. This is an old problem that you could apply to the management of your financial portfolio when you're thinking how to hedge over possible financial assets. This problem, this problem with the growth, maximization of the growth rate with aggregate risk turns out to be equivalent, mathematically equivalent to the standard model of rational inattention, to the discrete version of rational inattention by Maciek and McKay. You have seen it many times, but just let me go over it again just to clarify the notation. Rational attention problem is a very different problem. Again, it's a problem of a one person that is trading off the benefit and cost of information. So that person is choosing some joint distribution of the states and actions, subject to a constraint that the distribution has to agree with the true prior distributions over the states. So she cannot change the distribution of the states, but she can correlate as she wishes her actions with the states at the cost set up to the mutual information. And she chooses some optimal correlation. So Q star, let Q star denote the optimal joint distribution in this problem. So I will try to find out that distribution somehow hidden in the solution of our growth problem. So for that, let me introduce the following Wells-weighted sampling. So just go around our population of people, at random periods, pick up $1 from a wallet from the Aggregate Wells, and check what was the state at that date when you have picked up that $1, record it, check what action the owner of this $1 that you have picked has done, and repeat that, do this sampling and learn this well-weighted sample distribution of the pairs of states and actions. Since I'm picking up people who have a lot of wells, this introduces correlation between the state and action just by selection. I'm oversampling successful people. At the given date, those successful people have done an action which was well adapted to the current state. So call that joint distribution that we have done by alpha star. Like the solution of the rational inattention, it will have some correlation which is fruitful for the optimization of the growth rate. But here is the result. If the mixed strategy in our growth maximization problem was optimal, was maximizing the growth rate, then this Wells-weighted distribution that you have learned is going to be exactly the solution of the rational inattention problem. So in other words, what happens if you look at those people who are just hedging, they are not learning, our individuals, they didn't get any technology of learning, they're just optimally hedging their actions on an aggregate level. If you will be checking up on successful people, they will look like they have acquired information in an active learning, in a rational inattention problem. They look like exposed as if they were carefully weighting the cost and benefit information under specific information theoretic cost. But it turns out that if our model describes the true process, this is all generated by selection bias. No, please do. There are not enough of them. So
in I think Lumi's lecture, maybe Rafa also mentioned some, not today, but this some algorithm, Blackwood,
yes.
How is that connected to this third point?
So it is not directly connected. The Blackwood-Arimato algorithm is the algorithm from informational geometry. You take two sets of distributions, and you're looking for a pair of distribution, one from one set, other one from other, which minimizes the distance between those sets in terms of Kullback-Leibler divergence. That's what it is in general. It can be used as a solution to Kelly's problem of finding an optimal portfolio. It can be also used in finding solution of rational inattention. It's not surprising that it works in both cases because those two problems happen to be. So Blackwood-Arimato is.
Numerical way to solve this problem.
I think it's a bit more than that. It's a statement. Okay. Yes, it is used as a numerical method. I think it's deeper result than that. It's a result from information geometry. Yes, please, Jeff.
So you have a particular objective function that the investors have. That given that particular objective function, you have entropy. Now, I was wondering that this Morrison-Strach paper of years back presents for particular stochastic differential equations in terms of the instantaneous cost of learning to get this particular representation of the cost of attention in terms of final signals. So I'm wondering if there might be some way to do something similar here, that you have maybe a different objective for the investors,
Right. So let me slightly reformulate the question. So we've got it many times. So if you just start with a very natural growth process, and you are multiplying random returns, and then you are hedging optimally, then this solution can be represented as a rational inattention problem with a very specific cost, with the entropy, because we didn't assume it just shows up in this
Right,
case.
this is the most natural one. I'm asking as an extension.
And then the natural question is, are there some variants of the growth process? Maybe you are not multiplying, maybe you're doing something else. You shouldn't be adding probably, because then the large deviations have no role. And so are there natural versions of the growth processes that lead to different versions of rational inattention, or the rational inattention with different costs? And we tried to think about it. We didn't find the natural versions of the growth processes, so this is an open question. I don't know. Yeah, please.
Just like on, okay, I
Thank you for all the questions. So this is good for me.
I get all the mathematical risks, but like, I mean, like, really, do you connect these problems at a more kind of, like...
So you are asking about an interpretation.
What are
right.
the equivalents in terms of...
Yeah, so we let the reader to interpret it. One thing that we shouldn't do is we shouldn't claim that we have found a micro foundation for the entropic cost. It's this is a dynamic process. This specific correlation that would come out as an optimization under entropy cost comes if you are sampling according to the Wells or success of these people. But this also has a biological interpretation. So maybe it's not the Wells, it's the number of the kids that its populations might grow. So you would see the similar. You can have biological interpretation of the exercise. But it is not a problem of an active learning. And I think the economists working on rational attention are traditionally thinking about an active information acquisition or information processing. So this one is very different. It's a dynamic structure, and then a correlation appears out of some selection process. So it might be the case that a very careless econometrician who is collecting data and thinks more about Switzerland than Senegal, because Switzerland is just very rich, will come to a data set that will look like it was generated by rational attention, but it was just a careless work of a data collection. So that is one of the possible warnings, that the selection biases may actually lead to things such as that look like active learning. The biologists informally understood the connection between hedging and learning. So in biology they talk about what they call the bed hedging. So imagine you are a seed of a plant in a desert somewhere in Israel, and it is very important for you to start to grow at the particle time where the rain starts, because if you miss that moment, then you are out. Now, you don't have any radar, so you don't have a weather forecast, so you cannot actively acquire information about this important state of the world, which is the beginning of rain. So what do? As a population, you can hatch. You start to randomize. These seeds randomize, and some of them will then end up growing exactly when it's raining, and these guys exposed, the ones that led to trees, they all look like they have done a very informed action. So the biologists have understood this thing. They did not understand the exact connection between the particular information acquisition under a specific cost. Good. So let me give you an intuition why you get the rational inattention. So in the case of aggregate risk, all of us are experiencing the same sequence of shocks. And that's very different from the idiosyncratic risk when each of us was experiencing a different sequence. It was continuum of us, so some of us have experienced very lucky, atypical sequences. Now you cannot rely on deviations of this over the shocks. So all of us are experiencing most likely the typical sequence of shocks, but it's a continuum of us, and some of us might experience a lucky correlation between our action and the state. So it's kind of a story of a Forrest Gump who happened to be by accident always in the right place at the right time. There are not too many of those very lucky people. The measure of them, or the ratio of them, decays exponentially, again at the rate equal to the Kuber-Leiber divergence between a particle deviation and the Drew distribution. But that trade-off between the amount of luck that translates into an extraordinary growth rate of wells and the rarity of the large deviation happens to be mathematically exactly equivalent to the trade-off between the benefit and cost of information in the standard rational inattention problem with entropy cost. And that actually ties to this formulation of mutual information. This is exactly the Kullback-Leibler divergence between a joint distribution with some non-trivial correlation. This is the information structure where theta and x are independent. Since those people are randomizing without any active learning, their actions are independent the actions are independent from the states, but a subpopulation that diminishes at this rate happens to have a particular empirical correlation. This is why the mutual information shows up in our problem. Yes, please.
What is the interpretation for this wishful thinking outcome?
So in the wishful thinking model, in the psychological version of it, you dream of getting very good sequence of shocks, or a very good shock. There is no sequence, just one shock from some very good distribution. In the gross interpretation, there are really many of us. Some of us, maybe Elon Musk, will enjoy a very nice sequence of shocks. And then it turns out that those people who are experiencing those very nice shocks, they end up owning a lot of wealth. So that's the connection with the gross and wishful thinking.
It's more about, so you're telling very good stories like the selection bias may look like active learning.
Okay, yes.
Is there something similar for this wishful thinking?
Yeah, yes, it is very similar. So the selections are those people who become rich, who are winners of this growth process, who end up owning the wealth. Those are atypical people who experience atypical sequences of shocks. And those sequences of shocks, the distribution they are experiencing, they happen to be, the empirical distribution happens to be the dream distribution of the wishful thinker in the representation. Yes, please.
For the case of aggregate shocks, is there any value to thinking about trying to maximize the activity of the actions?
So you are asking whether you would max. So no. So this growth problem is represented by a classical rational attention. You are free to choose any mixed distribution. What happens is that, okay, let me just flip to my setting with. Sorry.
I'm thinking if maybe you want to increase the number of atypical sequences.
If you increase
Increase the number of atypical sequences.
number of
Atypical sequences.
let me try to give you an argument why that wouldn't help. Like, let me go back to my expression for. This one. So suppose you want to. Suppose the optimal correlation, the empirical correlation, which is supporting the growth in this, the growth problem with aggregate shocks, is this one. And then you are thinking about the mixed action that together with the distribution of the states makes this deviation as likely as possible. And you are free to, you cannot choose the distribution of the states, that exogenous, but you are choosing the mixed strategy. So you are choosing, this is A in my notation in that model, so you're choosing this. And to minimize this distance, what you would do is you would choose the PA, which would be just the marginal distribution of the actions from this joint distribution. So whatever is the optimal correlation structure that kind of supports the growth in this problem, the mixed strategy that is fitting it the best is going to be the true marginal action distribution. So you don't want to fiddle around with that. You're not really thinking of the deviations of the marginal distribution. All the deviations are happening in the correlation structure. let me give you a scam analogy. So there is a kind of, I have a favorite scam. I don't know whether this scam was really done in real life, but it is so elegant that perhaps it should have been. So here is how the scam works. You send out 64,000 letters to people with predictions of market going up or down next week. You have no idea about the market. So in the elementary version of this scam, you are just sending to half of those people a positive and a negative prediction. Half of the sample of the recipients get the correct prediction. You follow up with them, so now you have half of them, 32,000. So you send them again predictions and you divide it by half. Again, half of those get the correct prediction. Repeat 6 times, and if I didn't make some elementary mistakes, you end up with the 1,000 of recipients who received 6 correct predictions in a row. They must be very impressed, so then you sell them the 7th prediction, even though you have nothing about the market. And so what this story tells us that it is possible to pretend that you have an information structure without knowing anything. It just takes very many letters. Now in our model, there was no true information structure. These people were just randomizing their actions. But it took very many people, for the lucky people, to have an information structure, but those actually end up winning the growth rate because they get a growth advantage. And there is some element, there's some intermediate level of luck, which gives you enough of growth advantage, but it's not too rare, and that's the one that wins. So it's like a competition of all these scams where the most optimal one wins. That's the intuition. Again, you get a connection between the decision theoretic representation and the elements of growth that might be of interest for you. So what is an information expense in rational attention then becomes the rate of concentration of wells in our growth process. And what is an optimal distributions or information structure in rational attentions become an actual joint distribution of the states and actions of people who end up owning all the wells in our model. So just to wrap up this part of a presentation, stochastic growth might be kind of entertaining from the mathematical perspective. If you are multiplying random variables, then unusual things happen. You shouldn't rely on the law of large numbers. Large deviations become important. These things would not happen with additive objectives. So this is something which is kind of relevant for growth processes. Stochastic growth leads to lots of inequality, which was well understood in macro. So if you care about these things, then this is a beautiful literature review that you should read. And it turns out that the information theory can help you to understand why this growth inequality arises. It can inform you in a bit of a more detail about the aspects of the dynamics of wealth accumulation and inequality. There are also some tricks. You can take the technical insights from rational attention, and you can use them to find new things about optimal hedging or the optimal portfolio management, and I'm skipping those. So that was the one little part of the presentation, and then let me do something more traditional. Let me talk about rational attention. I will present a paper that Luminita has presented to some extent. I'm going to emphasize the aspect of rational attention that might be relevant for those of you who are thinking about some empirical work. So there is kind of a good match between the rational attention done with entropic costs and empirical practice that relies on logit choice functions, and I want to kind of advertise that match, or it might be something that some of you might find relevant. How am I doing this time? So okay, very good. So that might fit. The big picture that I want to emphasize is that when we observe people's behavior, well, we tend to conclude that if people do something, they like it, they have a large utility out of it. Now, there might be other reasons why people may do their choices. Maybe some of these choices are kind of more attractive, easier to think about. Maybe some choices are simple or default choices, and then people might just do it out of the fact that they don't like reasoning, and just going on the automatic regime might save them some reasoning costs. And if you don't think about these things carefully, then you can confuse incentives with some behavioral frictions. And here the rational attention can help to disentangle those things from the data if you are willing to make very strong assumptions about the underlying costs. So there are some empirical papers with structural estimation which are good for an illustration. So for example, this paper shows that people tend to retire at the default age of retirement. So many countries have some freedom in when you retire. You can go early or late, and depending on your personal conditions, this might be a good idea to not to retire at the default age. There are some incentives with it. So of course, retiring early is connected with penalties, but it might make sense to do it. Yet it happens that most people, very many people, retire at the default age, and when the government changes this default age by a year or two, the people's behavior change a lot. People just like to retire, or they happen to retire very often at the default age, and if you just fit the data with the standard structural estimation, then you get that people are very insensitive to the penalties that are associated with early retirement, and that's puzzling. And it might be the case that that is also misleading, that maybe people are retiring at the default age because that's just a simple decision to do, and they like to take simple decisions. And here the rational attention might be useful to disentangle those kinds of considerations, which is of course important for a government that tries to figure out what will happen if they will change the default rate, or if they will change the incentives related to the retirement system. So I want to give you a perspective of rational attention that emphasizes the behavioral biases associated with the defaults, and so I will just kind of give you again another introduction to rational attention with this particle perspective. This is Matejka and McKay again. So this is, let me start with the static version of this problem. So I will just explain the defaults, how they happen in the static version, because that's simpler. For the empirical work, a dynamic version of rational attention might be useful, so then I will extend the static version to the dynamic one later on, but the conceptual points can be made in the static one. So again, what was happening? There is some exogenous prior over the states. You are choosing a state contingent stochastic choice rule, so choosing a distribution of an action for each state. That's your control. You have a payoff function which gives you a reward for any combination of action and state. And you could correlate your action with the state and choose optimal action in every state, but that would be costly, and that trade-off between the cost and benefit is captured by mutual information. And we are interested in the optimal stochastic choice rule that tells you what is a good compromise, what is the stochastic choice rule that gives you high enough payoff and it's not too costly. Let me talk a little bit about predecessors of rational attention. You have seen this picture. So this is the picture used to illustrate the coding theorems from information theory. So just a point to made here, rational attention is really taken from information theory. It's a reduced form of what is called a rate distortion theory, where the rate distortion theory will go into the lengths of explaining why two people communicating over a noisy channel can achieve some correlation between the message and the output of the communication. What the economists did is that they took this problem, they took the characterization from information theory and applied it to economic environments. There are some warnings associated with this. The way this is done in information theory, when you really want to understand how this communication happens, is that the sender in this communication problem is not sending individual stimuli, but is sending sequences. And we now may understand why is that the case, because the sequences of random variables are much more predictable than an individual realization of a random variable. And so this motivation by communication, which was the original motivation for rational attention, makes a better sense when you're thinking about communication over the sequences than communications over the individual states. So there is a bit of a tension between the original import from information theory and the way we use it. Let me conclude this slide with an advertisement of really great textbooks by Cover and Thomas. So Cover and Thomas, Elements of Information Theory, is a classical textbook of information theory. It's really amazingly well written. So it's very precise mathematically, but very accessible, very deep. And there are many great economic ideas. They are not presented exactly for economists, but if you read carefully, you can find them. So I encourage you to read these textbooks. And I didn't tell you, but it is available on the internet if you Google enough. Let me tell you about another predecessor of rational attention, which is less known. So it's a relatively little known paper by Matson and Jorgen Weibel in Games and Economic Behavior, which is not exactly rational attention, but it's pretty close. So what they do is that they focus on a complete information problem. So rational attention is a problem of incomplete information. You're acquiring information structures, you're forming your beliefs, etc. This is a much simpler problem. There is no source of uncertainty. You are given a utility function, you would like to maximize it. Of course, you just choose a deterministic optimal action without any friction, but there is a friction. What these authors assume is that you are given an exogenous default rule, which is just a distribution over actions. And if you do not impose any control over yourself, this is what you end up doing. So it's a story of a trembling hand when if you do not really try to think very hard, then your hand will determine how often you choose right or left. And there is some exogenous distribution of right or left. But you are free to control your hand, so if you really want, you can always choose right or always choose left, but that's going to be costly, and the cost is again here given by the Kullback-Leibler divergence between the default action distribution and the one that you choose, so you choose a compromise action distribution. Now, what happens is that the solution of this, that this is just simple optimization problem, is a logit rule. It's an action distribution that tends to choose an action often if that action gives you a high payoff, but it's also biased towards the default action. So if your automatic mode of thinking says right is something that you are doing often without control, and left happens to be the optimal action, you still will be kind of doing a compromise between choosing left often and high often. So you're biased towards the default. Now it turns out that the rational attention, which is a problem of incomplete information and information acquisition, that's how it was kind of motivated, is equivalent to that control problem from the previous slide with a two-stage optimization. So in the first stage, so now we are back in the situation where your payoff depends on some payoff state theta and an action A, but unlike in the standard rational attention, we can imagine the decision maker who perfectly and without any friction observe the realization of the state. So suppose you're supposed to announce the outcome of a coin flip, you perfectly see the coin flip, and if you announce it correctly, you get $1. But you do a two-stage optimization. First, before seeing the outcome of a coin flip, just knowing the distribution of the coin, you choose a state-independent default rule that tells you how often you announce head or tail. I mean, that's your automatic system. And then you choose a state-dependent choice rule that, after you observe perfectly the state, tells you what is the action distribution. And you are optimizing this objective, your expected payoff, minus the control cost. So this is the expected payoff given your true stochastic choice rule given condition on the state. But in each state, you are paying a control cost from the deviation from your default rule. And when you solve this, the solution of this happens to coincide with the rational attention problem, which was motivated originally as an incomplete information. This turns out to be a complete information problem, and that happens to be relevant because it's easier to extend into dynamic setting, which we will be doing later on. Solution of this is a fixed point. So the stochastic choice rule, the state condition stochastic choice rule will be given by this bias logit, which is biased towards your default rule. The optimal default rule will happen to be just the average action distribution given your state condition stochastic choice rule, you take an average with respect to the payoff state. So you're looking for a fixed point where your automatic system is the average of your true behavior, and then your behavior is an optimal deviation from your automatic system. If you solve that, you have solved the rational inattention problem. So this has an advantage in that in Matson and Weibel, the default rule was exogenous, so we didn't know where it was coming from. Here, now, when you understand the incentives of the person, then you can compute the optimal biases of the people or of the person, or if you are observing the stochastic behavior of this person, you can deduce what part of the behavior is driven by this pseudo behavioral bias and which part is driven by the incentive. So if you believe into this model, you observe the stochastic choice data, you are doing the logit estimation, you can separate the part of the behavior coming from this information theoretic inspired bias from the true incentives. Once you have estimated the true incentives, you can then ask what happens if I change the action set or the payoffs, etc. You can do counterfactual analysis. So we have extended this to a dynamic problem. So let me briefly tell you how the model looks like with the dynamic extension. It becomes a bit cumbersome, but it is conceptually quite similar. So there are some stochastic process of payoff states that you can learn about by acquiring information repeatedly. You are making decisions repeatedly, so now there are many periods in discrete times. You are doing choice at any given time. You can choose a stochastic choice rule, which is now a bigger object, so it determines an action distribution at any given period theta, conditionally on the whole payoff state history and conditional on the action history. So all the upper indices indicate a history, lower index indicates a particular realization at a given period. So this is the object that kind of generalizes the state-dependent stochastic choice rule in the static case. This is what you are looking for. You were given the prior over the sequences of the shocks. You are maximizing some discounted sum of flow payoffs minus the cost of information in every period, where the cost of information is given by the mutual information between the action that you have taken in a particular given period and the whole state history. So at any state, at any period, you can learn about the whole history of shocks at a cost, and you remember all the information. So unlike in Ravestock, you have a perfect memory in this model. You remember every information that you have learned before, and this is why this mutual information here is conditioned on the action history, because that kind of encodes all the information that you have acquired up to now. So this is an extension of the static rational attention problem. It will be difficult to solve by dynamic programming. You would have to track the evolution of the belief. And so the way we have solved it was by translating it into a control problem, which is a complete information problem, which is easier to work with dynamic programming because you don't have to track beliefs. An example of a setting is just simple tracking problem. Maybe you are tracking a Markov chain, say binary. If you guess the current state correctly, you get $1. Otherwise, you don't get $1. So it may be as simple as that. As in the static case, this can be translated into the dynamic control problem when you have two rules. One is a coarse rule that you have to choose at the ex ante stage when you are not informed, you're not allowed to really look into any realization of the states. You are only knowing the distribution over the sequences. So this is some kind of an automaton that tells you how likely you are choosing an action, a specific action, given an action's history. So this automaton can now condition on the previous actions, and that couldn't have been discussed in the static problem because there was no action history. So now, given that, you can ask, will there be an inertia in my behavior? So will it be the case that I will have a tendency to repeat the previous action, or maybe I will be switching actions a lot? This can be summarized by this endogenous default rule, which is blind in the sense it doesn't observe the states, but it can freely condition on the action history. And then in this more refined stage of decision making, you are choosing a stochastic choice rule which conditions the action distribution in any given decision node on the action history and the history of the state. So this one is refined. Here you can think of this as observing the states perfectly, all the state history. It just is difficult for you to deviate from this automatic regime. So we've written the original problem, which was again formulated as information acquisition, as a two-stage control problem where we are choosing this automatic default rule and the non-blind refined rule, maximizing the payoff given your behavior under the refined rule, and paying a cost for any deviation at any action history from the default rule. So whenever you do something else than your automaton is suggesting, you are penalized for that, and you can choose your automaton. Solution of this, so this is a translation of an incomplete information problem to a complete information problem that I can now solve for each shock history separately. And this, like in Matson and Weibel, the solution of this is relatively easy. It turns out that this solution of this control problem, once you fix the automatic rule, the default rule, is a dynamic logit choice rule, something that has been introduced by Rust and which is extensively used in structural estimation, where Rust has motivated that by a random utility model with a specific distribution of shocks. Here it shows, again, with an important caveat, given a default rule, the optimal choice rule in our problem is this Rust dynamic logit, but not with respect to the true utility, but with respect to a modified utility where the modifying element reflects this automatic default rule. So you are biased towards an action recommended by the default rule. If the default rule recommends you a particular action with a high probability of any action history, you behave as if you had a preference. So the Rust, looking at your data, would conclude that you are behaving as if you had a preference for following that default rule. So in particular, if the default rule would be repeat with high probability or past action, Rust would collect the choice data on you and would try to explain you. Rust would conclude that you have an actual physical switching cost. Now the real story for you, having an inertia in your behavior, might be information theoretic. So if there are serial correlations between the incentives, between the payoff shocks, and if yesterday you have kind of optimized your behavior, then your past action is a good hint. It's a kind of first approximation of what is the optimal action today, and it's cheap. You remember, you have perfect memory, so if you remember what you have done yesterday, your first hunch might be to repeat it, and this is kind of formalized in this model where the optimal default rule in a setting with serial correlations of incentives will exhibit inertia. You will then show up from the perspective of Rust as having a switching cost, but that might be misleading because that switching cost in our model is endogenous, and if incentives change or if the serial correlations change in the environment, then the switching cost that Rust is estimating as a part of your actual utility will be modified and changing for whatever intervention you are subject to. The second condition, so again, the solution is a fixed point. Question?
Question about the setup. Does my action influence the transition probability, or
We have that, so we found, so our first version of the paper didn't have that possibility, so you could not actively control the environment. We were asked to do it, and we found kind of a formal way of rewrite by introducing some fake states of the world that made it, we could accommodate that.
But this version on the slide
The version of the slide does not, but there is a way of translating your problem into a bigger problem with larger larger state space in which you do not control the environment and thereby solving it. Thank you for the question. Yep, you, oh, good. Again, the solution is a fixed point. So looking for this state condition choice rule that optimally deviates from the default rule, from our automatic regime. And the optimal automatic regime is just the average of your true behavior when I have now integrated here from a true stochastic choice rule the random pair of states. So it's a difficult fixed point, but can be solved. Please.
Very naive question, but I'm just surprised there's no parameter
The marginal cost of information, or the scale of the cost, or?
Yeah, no, just with the second term in the utility function. Like how
yes.
much we rely on the default.
Very good.
Yeah.
Why is that so? Because I didn't bother to write a scaling parameter of a cost here. So typically people write here some scaling parameter, say lambda. I don't think it's very necessary because you can also rescale the utility functions. You can just normalize the scaling parameter to 1, and so you get rid of one letter in your equation. That's the answer. So I have hidden it into a utility function. Okay, thank you. Right, so one thing that this model can do is can help you to think about habit formation. So if you are in an environment with more serial correlations, then choosing a default rule that suggests to follow your previous action seems like a good idea. If the serial correlation becomes weaker, then maybe your past action isn't very informative of the current optimal action, and so the default rule will exhibit less serial correlation. Again, this couldn't be done with the standard logic where those serial correlations in our behavior are explained by a cost, which wouldn't really change with the change of the stochastic process. In my one and only experiment with Ludmila Matiskova, we have verified that in a laboratory setting where we have been manipulating the extent of serial correlations, and we looked how the inertia in actual behavior changes, and qualitatively it works. Let me perhaps conclude this part with just an advertisement of one particular aspect of rational attention, which turns out to be attractive for empirical people. I thought that they would be attracted by this treatment of biases towards defaults. What attracted them, and there were some recent job market papers trying to applying this successfully to the data, was that, to my surprise, the problem with the rational attention problem, or the fit of the rational attention model to the actual data, is easier than applying Rust model. I thought it would be more difficult because this involves a fixed point, whereas the Rust doesn't. But there is one aspect of this problem which makes it friendly for practical use, and that is that in tracking problems, say that you are tracking a Markov chain and you are rewarded for announcing the correct state today, the optimal choice rules in our model will have a very short memory. It turns out that the optimal choice rule in this particular model, in a tracking problem where the Markov processes just memory 1, will condition on the past action but not on any previous actions. And that would not be the case for a conceptually simpler model in which information is exogenous. So if you are tracking a Markov chain and every day you are receiving a signal correlated with the current state, then your belief about the current state is going to be influenced by all the signal history, including the signal 10,000 years ago, and that's a pain to track. It's a pain to work with. This is why, if you have to program it, that's not very pleasant. So it was this this appealing simplicity of the optimal choice rule that was attracting the structural estimation people. I have decided not to explain why exactly this is the case, why this simplicity of the optimal rule shows up. This is not driven by the entropy. So this is a more general property. For those of you who are working on rational attention, this is implied by posterior separable cost function. To understand why this shows up, you would have to think about the problem from a different perspective, which I think you haven't been exposed to. You would have to take Kaplins and Dean's perspective on rational attention that emphasizes posterior information structures. But the good news is it is a robust property that will hold for much larger class of information cost not only for an entropy. And if you will be ever thinking about these types of problems, then we can talk more about why this property holds. So let me just wrap up this part, and I will use the last 10 minutes to introduce the other part of my talk. So what I wanted to emphasize is that with a particle information cost, a very specific one, you get an equivalence between the rational attention model, dynamic or static, and a control problem. You get choice rules which are logic choice rule, either static or dynamic, so they match very closely what is being done in practical structural estimation. You get some sense of what behavior might be driven by behavior biases that stem from optimization of information acquisition, and what is truly driven by incentives, and that might lead to useful comparative statics relative to a model which ignores informational aspects of the decision problem. And that was the main message I wanted to convey in this part. And so then my last 10 minutes maybe will be devoted to something which I think which will be very related to what Rava did. This will be slightly different in this spirit. I will be talking about encoding and decoding of information that brain connects about incentives about your environment, and how this might or might not relate to our risk attitudes. So let me start with an analogy which is popular in particle literature. It's an analogy between a measurement problem as done by engineers, and the measurement as done by people who are considering how attractive various options are using some curved utility function. So think of an engineer who is measuring some physical input. I think this was something with electricity. The scales that are being used are not entirely uniformly reliable. So there might be some parts of the range of inputs where the reading of the measurement might become quite unreliable. There might be some accurate reading area in which even if the needle that you are reading off is trembling a little bit, will give you a pretty good information about what the actual input that you are trying to measure is. And the way this is being done is that, of course, the engineers set up some non-linear function that translates the measured inputs into the needle position, and that function is somewhere steep and somewhere it's quite flat. The physical constraints do not allow this function to be steep everywhere. And first of all, if you would have no friction in reading of the position of the needle, if the needle wasn't trembling and if it was infinitely thin, then you wouldn't care about this monotone transformation. Any such monotone transformation could lead to perfect measurement. But once the needle trembles, then imagine a specific tremble of the needle here with certain variance. Well, the same uncertainty about the needle position translates into little uncertainty over the input if this function is steep, and translates into large uncertainty if this function is flat. And so then by controlling this function, by making it steep for a particular range of inputs, you are improving your ability to measure that range of input on the expense of your ability of measuring other ranges of inputs. And so an analogy has been done by many authors that similar kind of adaptation to our measurements explain the curvature of a utility function. In particular, it's appearing to say that the S-shaped utility function in prospect theory might be an optimal adaptation, which makes your utility function very steep around the status quo, because maybe this is the range of stimuli that are important in your decision making. And so we are exploring this idea in a formal model, And we are saying that under some conditions, these types of adaptation of your measurement of various stimuli might have to do with your risk attitudes. In certain other situations, they might not. That will be the message of the paper. And I will not get very far because I think I have 5 more minutes. So let me see how far I get. This is a picture from a work of my colleagues in Zurich. So we have a brain science lab in the building. On this axis, there is a contrast, some sort of a stimuli that lives on a real line that the fly has been exposed to. On this axis, you have some normalized neural activity of that particular fly. The dots that you don't really see very much because they're hidden behind the curves are the actual data. The 2 curves that are being fit are optimized such measurement functions under some models that I will explain more about. One of them is a popular model in brain sciences. The other one is a model by Nick Netzer, a co-author also of this paper, the paper in AR maybe 10 years ago, where the difference is that the Infomax model assumes conceptually that what the brain of the fly tries to do is to retain as much information about the stimuli as possible. The model of Nick being an economist, says that the way the measurement function is adapted is such that it helps the fly to do the decisions as well as possible. So there is some decision-making process behind the adaptation process in this paper. It turns out that empirically, at least in this paper, the economic model wins. It gives a better fit to the data than the traditional brain science paper. I just wanted to convey that these measurement functions have some empirical content. They can be to some extent measured, and so you can test those models. And what we are asking in this paper is whether the curvature of those measurement functions, that is a function from some stimuli to some neural activity, whether these things have implications for risk preferences, for risk attitudes of people. And this is not clear at all, because so far the models of this kind of neural representations, both that Rava represented also on these pictures, they don't involve any lotteries. So it is tempting to think of these as of utility functions or S-shaped utility functions from perspective theory, but here the input is just one-dimensional stimuli, whereas lottery is a more complicated object. So what we do in this paper is that we take lotteries more seriously. We give the decision maker an access to information about lottery, and we are asking how is he or she collecting data about lotteries, how encoding and decoding might be done, and what are the implications of that in the context of explicitly modeled risk. Now, what we find out is that you might need some additional frictions for this encoding and decoding having a bite, having implications for the choices of risky prospects. One of such additional frictions that might matter might be large noise, and this is what has been done by Mike in some of his recent work, where this encoding and decoding is sufficiently noisy so that information is substantially lost. Now, we are looking at this paper at a limit where so much information is being collected and the decoding is so sophisticated that there is very little information loss. And we are asking whether in those situations where we are nearly close to perfect information, the encoding and decoding process might have an implications for choice over risky prospects. And now it depends. We find out that without an additional friction it does not, because you don't lose any information, you are sophisticated, and so you end up observing the values of the lottery perfectly, and then this is not a way of helping us to understand the risk attitudes. But then we then add one layer of naivety at the decoding stage, and then we find out that actually those brain science considerations might have a close connection to risk attitudes. We think that looking at the limit of nearly complete information is useful, because if the stakes are large, and and we want to understand how people do decisions over large stakes, then the frictions that are relevant in this process should be small relative to the stakes. And also doing the limit is relatively analytically tractable. So this is what I will continue with tomorrow.